Thank you very much, Mark. It's a great pleasure to be back with you again. And I'm going to talk on my third topic in this lecture. And I think I introduced the last lecture by saying it was probably going to be the most phenomenological and astronomical of them. This one, I think, is probably going to be the one with the most physics content, although in practice, the physics is quite old-fashioned. But the application is quite new and rapidly developing. So let me perhaps try to share my screen. And I think it's this one. And you should see,
yeah, we see it.
You see it, and then when I just play from start, I'll just do it like that. Okay, you should see it now in full screen again, I think.
Yeah.
Perfect.
Okay. Okay, can everyone see that? Is that okay?
Yes, it is.
Okay, good. All right. So I'm following the pattern which I developed last time, I suppose. I'll list some of the people I've talked with about what I'm saying here in terms of my own collaborations. There's obviously a much larger community who are thinking about this topic. Some of them, Ted Sharland, for example, my research has gone back over 45 years. Others are much more current. And as I've said in the past, none should be blamed for some of the ideas I'm going to share with you. And I'll try and distinguish when I'm sort of dealing with what I think is commonly accepted and when I'm going a little bit off the standard path. So I'll try and distinguish that so you can have my government health warning, if you like, at that point. Okay, and as I did last time in the pattern, this time I'm not going to show old historical figures. I'll show some of the quite often somewhat young people, not all of them, who are most of them observers who should take the credit for what I believe is a very fascinating development in astronomy with genuine implications for cosmology and indeed physics. So just for the top left-hand corner, I think there's Jocelyn Bell and Tony Hewish, who discovered pulsars in 1967. They weren't the first neutron stars discovered in practice because X-ray astronomers had been looking at them for a few years earlier without realizing it. For me, this is, I was actually an undergraduate at the time they discovered this, and I think I may have said this before, that I was in the astronomy club in Cambridge and heard one of the first talks about this, and it was extremely exciting as a new discovery because it rapidly became clear that they were indeed looking at spinning magnetized neutron stars. In no particular order, and these are just a sort of eclectic selection, two people next on the right-hand side who made a sort of bold conjecture. That's Chris Thompson and Rob Duncan, who made a bold conjecture that were a subset of neutron stars. I'll say a little bit more about this, that unlike the regular pulsars, which were traditionally then at that time associated with 100 megatesla magnetic fields, there were a subset called magnetars, which are 100 gigatesla magnetic fields. I think I mentioned this briefly, but I'll say more about it. And then another of my friends and colleagues, Krista Kuviliotou, who, along with her team, is an observer who said, yes, you're right. Next comes Duncan Lorimer, University of West Virginia, a Welshman there, and he and his student Narkovich found the first fast radio burst. Say a little bit more about that. Then bottom left-hand corner, Vicky Caspi, who has worked for a long while in many of these topics, but also has developed and led a Canadian telescope called CHIME, which has made a lot of discoveries in this area, along with the Australians. It was designed for cosmology, but it's really delivering all its results on compact objects. Here's Sri Kulkarni, who has led a similar effort at fast radio bursts, and his part in the story will come up. Vikram Ravi who's helping build the next generation of radio telescopes that will study these objects, and I'll say a bit more about that. Emily Petrov, who has made big observational discoveries, and somebody whose picture I wanted to show last time, who's almost incidental to the story today, but was not incidental to the story of the cosmic jet. So this is Francis Halzen, who, as you know, is a Belgian, and his sort of kind of connection to actually is also the first lecture, because he told me once that he was a graduate student in Louvain in sort of last couple of years of Lemaitre's life, and so he overlapped, in fact, with Lemaitre when he was in Louvain. And Francis Halzen has essentially led and developed this facility called Ice Cube at the South Pole, which has perhaps found PeV neutrinos from the jets, and he has failed to find neutrinos from the fast radio bursts, which is actually an important piece of scientific information. Okay, so let's move on. Let's just say a little bit about regular neutron stars. They, of course, are, you know, a physicist's playground. Neutron stars, you almost can't find a part of physics that isn't represented in one way or another in the context of neutron stars. The traditional ones that Bell and Hewish found originally about 1 to 2 solar masses, now 10 to the 57 nucleons. Their radius will be 10 to the 19, therefore Fermis or femtometers, which works out to be 10 kilometers, and that's pretty accurate. You know, a modern equation of state will give you 11 kilometers. They are relativistic objects with surface potentials of about a 10th c², which I'll ignore. Their traditional magnetic fields are 100 megateslas or 10 to the 12th Gauss. That's, you know, 3 trillion times the field on Earth. Their spin periods range from about 1.5 milliseconds to, as top E flat on the piano, to 30 seconds or so, and they're seen through radio, through gamma ray energies, and they're powered by the spin energy of the spinning neutrons, the rotational energy of the spinning neutron star. On the right-hand side, this is the charts strip scan from 1967, the first CP 1919, the first one found. So the most elementary model is you've got this magnetic dipole endowed in a neutron star spinning out its axis, and acts like a lighthouse, sending coherent radio emission along, more or less along its spin axis, and we see it if we're at the right inclination with respect to the spin axis, which is not all cases, but roughly about, depending on many other things, between 5 and 20% of the pulsars we will see in that way. As I say, they're a theorist or a physicist's playground, because they show us so many different parts of condensed matter, particle physics, electromagnetism, weak interactions, even particularly in their formations. Well, actually, it's quite relevant all the time, and all of these things show up in the study of neutron stars. I'll say almost nothing about this. For me, they'll just be dumb rocks that are spit back 10 kilometers in size that are spinning, and that's all I'll need for these purposes, except the fact that they're superconducting, and therefore they retain their magnetic fields extremely well, but they're very active in their interiors, particularly when they're young. So now before I get onto the fast radio bursts, let me go not the FRBs, but the GRBs. And I suppose the next astronomical discovery will be called an ERB, but I don't know what it is. But the gamma ray burst, this is a slide that I showed last time. Originally, they were discovered in 1960s, sorry, using satellites designed to monitor nuclear tests and so on. And they found all these bursts of gamma rays, which thankfully they're identified as extraterrestrial, and and although it was classified for a while, it quickly became declassified, and these were known as gamma ray bursts. and there were for a long while there were many more theories of gamma ray bursts than there were examples, and we now know that this is an important and not uncommon astronomical phenomenon. This class that was identified by observers turns out to be, now we're pretty sure, we're not totally sure, but just three totally different types of physical phenomena that can create bursts of gamma rays. The two that I emphasized last time were the gamma ray bursts, the long gamma ray bursts, which are basically massive star supernova explosions. So that's shown here in this diagram. Here we get a regular supernova explosion, and about 1% or so of these are going to make black holes and create jets which punch their way out of the infalling gas and make these jets. And with their beam towards us, then we see them as flashes of gamma rays and long-term afterglows after that. And then the short gamma ray bursts, again, it could be more complicated, but the simple view is that the 1708-17 gravitational wave event seen by LIGO was one of these two neutron stars merging, also giving jets, but a very different sort of physical phenomenon, and seeing gamma rays intensely when they're beamed towards us, and weakly, as was the case in 1708-17, when they're not beamed towards us. But the third type were the so-called soft gamma repeaters. And this is what Thomson and Duncan did. They identified these with these super magnetized neutron stars, which they call magnetars. And these we now believe to be, maybe not all, but a large fraction of very young neutron stars, perhaps within the first 100 or 1,000 years of their lives, which have these enormous magnetic fields of 100 gigatesla, 10 to the 15 Gauss. We'll come to that in a moment. And they were identified as being responsible for these soft gamma repeaters and one or two other types of astronomical source. And that turns out to be almost certainly the case. And the thesis I'm going to develop here is that is also responsible for that's also the site, excuse me, of the next topic, which is the fast radio bursts. So let me tell you what they are. They were discovered from looking at old radio data by Lorimer, whose picture I showed you, and an undergraduate student called Narkovich. They were discovered in 2007, and the actual burst happened in 2001. And they were actually looking for something different, but they had, like Jocelyn Bell, they had the wit to follow up something that was odd in the data, and then they found what looked like the first fast radio burst. Basically, they're radio phenomena. They're not seen, with one caveat, which I'll come to, but they're basically not seen at other wavelengths. And say Francis Halzen failed to find them in using IceCube, and several other people have failed to find them too. They observe, say, these radio wavelengths, and they have what radio astronomers call high brightness temperature. And again, I'll come back to this point. It's a sort of affectation of radio astronomers, is they like to measure the strength of their radio signals as a brightness temperature. And basically what that is they ask, well, what would a Rayleigh-Jeans spectrum with a given temperature, how that would have the same intensity, what would the temperature be? And then these temperatures, in the case of the fast radio bursts, are as high as can be, in the most extreme cases, as high as 10 to the 40 degrees Kelvin. And again, I'll return to why I think this is not a terribly useful way to think about them. They're highly polarized, typically, mostly linear, sometimes nearly 100% linear, and occasionally they're circularly polarized too. Again, that'll be a feature, not a bug, of what comes along, but they're like pulsars in that regard. Their intrinsic durations are sort of typically about a millisecond or so, but the structure in several of them on the scale of 10 microseconds. So, but if we want to think about them as ongoing events, and again, I'll say a bit more about this, they last for about a millisecond or so. And there's a very large dispersion in their properties. So just take these as fiducial numbers, but I'll use both these numbers, the fact that they sort of go on for a millisecond, but there's evidence of structure on the scale of 10 microseconds, which says they must have very compact sources. Now, one of the things that makes them a little bit difficult to recognize and study, but radio astronomers know how to do this sort of thing, is that there's they are cosmologically distant objects, and there's the plasma in the intergalactic medium along the line of sight causes a dispersion of the waves. So the group velocity of the low frequency waves is slightly less than the speed of light. And so when you observe over a bandwidth, you have to remove that effect, and radio astronomers have had a lot of practice at doing that. Another thing that happens is that you get scattering. It's the radio version of why stars twinkle in the atmosphere at optical wavelengths. It's the radio version of that. And that scattering, of course, is not easily not removable, but you can learn an awful lot from it. So that happens too. And then the plane of polarization gets rotated in a wavelength-dependent ways. This is called Faraday rotation. And what I'm not going to say anything about here, but I'm probably more bullish even than most of my colleagues on these, is that these are highly promising for cosmology. The observers are talking about millions, and some are even saying hundreds of millions or something of these sources being seen. And you can do a lot of cosmological measurements using them, even if you don't understand how they work, like pulsars, which have been tremendously important for physics, in a way that's independent of their mechanisms. The fact that you've got these distant sources fairly sampling the intergalactic medium, gravitationally lensing, and all of that good stuff makes them tremendously valuable for, I think, the future of cosmology. Now, if we take a canonical fast radio burst, nothing special, and put it at a distance, a modestly cosmological distance of a gigaparsec or so, then a characteristic energy would be about 10 to the 33 joules, which might sound a lot to you, but to a high energy astrophysicist is a rather small amount of energy. They are very common phenomena. This is not even clear quite how to define them, because it depends on how faint you look and so on. But if you had a telescope that looked at the whole sky and was pretty sensitive, then you'd see them going off about one a minute or so across the sky, and they're completely isotropic as far as we can tell on the sky. There's probably about 1,000 so far that have been well studied, and this is a point that is a very important clue. So for Thomson and Thomson out there, pay attention to, that's not our Thomson, it's your Thomson, 20 repeaters. And one of these repeaters actually is exhibited at what is now accepted, I think, as a significant 16-day period, indicating that it's in a binary system of some sort. Again, I won't say a lot more about it. I'll say a little bit more about it, but not a lot. Now, some of them have been identified. This has been a big development of the last couple of years and been shown to be in very different environments inside galaxies. There are huge clues here, especially for the astronomer. Again, I'm going to de-emphasize this, but we do know where some of them are located, and it's not a common environment. And it could be that there are many types of source involved, just as the reason why I showed the gamma ray burst slide was to emphasize that after things have settled down now to 3 different types of object, the same could happen here. But I'll take the Occamist view that, in fact, we're just looking at one generic phenomenon until there's compelling evidence that that's not the case. Just some of the pictures here. This is CHIME. This is the Canadian hydrogen monitoring hydrogen measuring device designed for cosmology, but it's turned out to be a fabulous instrument for studying the fast radio bursts. This is an artist's conception of a giant 2,000 telescope facility which exists in the minds of radio astronomers. So they've got 100 of these dishes already. The hardware for these things is relatively cheap and straightforward. The data processing is very sophisticated by comparison. Here's what I think is actually the first fast radio burst that was found, but it's a sort of typical one, a radio pulse lasting a millisecond. Here we see the effects of dispersion. At a high frequency, the pulse is rather narrow. At a lower frequency, the pulse is broadened. And here's a phenomenon which is another big clue, and I won't say as much about them as I should do, is that as we look in the frequency time diagram, sometimes called a dynamic spectrum, you tend to see the higher frequencies arrive earlier than the lower frequencies. And this is beyond the dispersion, this is intrinsically, so the higher frequencies are getting out of the source before the lower frequencies. That's an important clue. Again, I won't say any more about it. Now, in terms of explanations of these fast radio bursts, just as happened with gamma ray bursts, there were very many of them out there and they're still coming. The first explanation, which came from the radio astronomers, was that they were looking at radio interference. They were all just terrestrial, they were radio interference, and of course that was what was thought about from pulsars. And in most cases that's correct. An awful lot of the spikes and so on that are seen are just terrestrial radio interference, and this happens all the time, military aircraft and so on. And so the game is to remove all of those, and radio astronomers are very clever people, and they know how to do that. They know how to recognize it, know how to excise it from their data, and they're still left with radio bursts, these so-called fast radio bursts. It turns out, and you have to be a radio astronomer to realize how exquisitely embarrassing this is, but a subset of these remaining bursts were actually due to microwave ovens, and the tip-off was when it was happening at lunchtime. And a badly shielded microwave oven in an observatory produced what they subsequently called peritons after H.P. Lovecraft. And but now they can remove those from the data. And then for the extraterrestrial ones, there were a variety of ideas out there. Most of them actually came from physicists, underemployed theoretical physicists, I imagine, but not a small number came from astronomers. I don't know why this keeps on skipping around. Okay, the most imaginative may be departing aliens who've taken one look at us and decided to go away, and these are the light sails that they were moving through. Cosmic strings, of course, white holes, primordial black holes, various forms of a higher order entanglement in quantum mechanics, superconducting dipoles, ball lightning, strange stars, all of these wonderful things out there. And I think my colleague Mal Ruderman, in the context of gamma ray bursts, said, yes, he believed they were all right for one object. So I don't know whether that's true or not. And I think that the more serious astronomical possibilities, and I would say they should still be on the table, are active galactic nuclei, supernova explosions of one form or another, emerging neutron stars, and black hole binaries. And I just show this one here with this is a model that I heard in the talk yesterday, and I'm not going to say any more about it, but it's a black hole, a stellar black hole with a jet of the type we talked about in the last lecture, spinning and lens tearing precession of a disk with gas supplied by a companion star, is responsible for the 16-day period, I imagine. And so, and then the emission then comes from a jet going out from a black hole. So, people are seriously thinking about these possibilities. It should still be on the table, not the least because we could be looking at a bag full of many different types of phenomenon here. So it could be that this, a subset of them are really something like this. So one should not be doctrinaire at this point. Okay, so now last year there may or may not have been, history will say, have been a breakthrough, and that connects the two topics that I've mentioned. This object here is a known soft gamma repeater, 1935 plus 2154, quite forgettable name, and two groups, one facility that was sort of masterminded by Sri Kulkarni and the other by Vicky Caspi, which is CHIME, and they found a radio burst which they could identify with this soft gamma repeater, which is known to be a magnetar, known to be a highly magnetized neutron star. And whoops, wait a minute. But it's not quite the same thing. And so it's not clear whether there's enough circumstantial evidence to indict magnetars as fast radio bursts yet. But this is a diagram that's quite instructive. This is essentially the energy, if you like. It's this square the distance times the radio flux, and the fast radio bursts are in this group up here. This is a sort of essentially the number of wavelengths you're looking at, and this here is these are all the fast radio bursts, which are classified at the moment in one category. Here's the soft gamma repeater, which is somewhere in this region down here. So it's nowhere near as powerful as the extragalactic fast radio burst. This one is in our galaxy, so it's very close by. But it's much more powerful than the regular pulsars, which are down here. And there's, again, I'll come back to those again. These are other phenomena, don't worry about them here. So it's not quite clear it's the same phenomenon as that. And this one actually is a soft gamma repeater, so it actually makes X-rays, which the extragalactic sources don't see. And in very, very round numbers, the energy associated with the radio emission is about 10 to the minus 5 or so of the energy associated with the X-ray emission, and about 10 to the minus 4 or 5 of the energy you might associate with a bright, fast, cosmologically distant fast radio burst. But it did look like, as a radio source, it did look like a radio burst, albeit a faint one. And this is sort of guilt by association, if you like. And so we'll wait and see if this is really is a breakthrough, but it certainly encourages those who, including me. I mean, from the start, my guess was that these were magnetars, you know, from the first discovery in sort of 2009. So you can either put me down as prescient or a slow learner, but it's so I was quite encouraged, in fact by this. And I would like to say one thing, actually, that, you know, the magnetars really are the conservative explanation, and it is a comment on contemporary astrophysics that a 10-kilometer sphere of nuclear matter, that superconducting, superfluid, rotating with speeds that can be as short as a millisecond, or with periods as short as a millisecond, endowed with 100 gigatesla magnetic field, is the prosaic and conservative explanation. And so, you know, you just have to sort of pinch yourself after you've said that. Any rate, so let me say a little bit more here. Okay, so what are these radio bursts? I'm going to, in this talk again, de-emphasize what I ought to have emphasized in the past. In fact, it seems to have, maybe I didn't say it. No, okay. So somehow that seemed to slip from the side. So let me just make this very important point. Then it seems to have slipped out of my view graphic, unless it comes up later. Okay, I'll make this important point. The idea. Okay, let me make it in the context of this one here. Okay, I'll make it here. Yes. the magnetic fields that we're talking about in these highly magnetized neutron stars, sort of up to 100 gigateslas or so, that is 30 times the quantum electrodynamic or critical field, sometimes called the Schwinger field, when the spacing between the Landau levels for an electron in a uniform magnetic field is more than mc squared. So you're way up there in the nonlinear, probably collective quantum electrodynamical regime, which is one that is the target of light sources at the moment, is to try and get in that regime. Well, there's almost certainly new physics. This is not saying that quantum electrodynamics is in any way suspect. It's a gloriously successful theory, and in QED we trust. But when you get up into these highly nonlinear, non-perturbative cases, it's not entirely clear how to calculate things, and there's the real possibility of new collective many body type effects there, and they could be operating under these circumstances, and they could be accessible from the next generation of light source experiments and so on. So just leave that there as a thought. At any rate, if we try and think about these fast radio bursts, then the basic idea is that maybe the problem is, I think this is the problem. Yes, I think a slide has got out of order. That's the problem. Okay, so let me show this slide and then I'll return to the previous slide. I apologize for that. Okay, so so this is where I said that the field is about up to 30 times the Schwinger field, and under these circumstances, you just have to realize that it's very, very easy to make electrons and positrons. For example, there are many QED processes that will do the job for you, and you can argue about which of them is the quickest and fastest. But a gamma ray passing by a magnetic field line looks at the perpendicular component of that magnetic field line and sees a low frequency electromagnetic wave, and under these circumstances makes pairs prodigiously. And so the point is that you will make pairs, electron-positron pairs, and from an electrodynamical point of view, the vacuum is essentially perfectly conducting. If you put a little bit of electric field there, you will have charged particles removing the charge differences, and currents will flow with essentially infinite conductivity. And now the idea with the radio bursts that almost all of us who think about magnetars have latched onto is that these magnetars, which are almost certainly very young neutron stars, will have very complicated magnetic fields. Shown schematically here is what the surface radial field might look like, and here's the field lines associated with them. So it's just like the sun, which we see down here with these complicated coronal loops and so on. And motions in the interior, crustal motions, and indeed even instabilities that can happen at much greater densities at lower depths, can either stress these magnetic fields, sends currents along them. This is the sun, and the bits that are illuminated are the bits where the field lines are twisted and there's a current flowing along them. And they're twisted because of what happens at the foot points on the surface of the sun. And so then they twist them, just like twisting a string or something, it will eventually go unstable and convert to a lower energy state, releasing an awful lot of energy. So that sort of solar flare type thing scaled up to a magnetar is what is assumed to happen here. As I say, it could be due to either a slow surface twisting to a point of instability, that can happen, or it could be, as I say, some interior starquake. Again, I mentioned Mal Ruderman. He always used to say this subject should strictly be called astrology. It's not geology, it's astrology. And so you look at the these field lines, and then you'll have this impulsive magnetic flare. It's going to make wavelengths, disturbances in this electromagnetic field. I'll discuss those in a moment. And those are going to send waves which you can make various computations of. Say here, 2 waves going out from a disturbance on the neutron star going way out into the magnetosphere. And just like disturbances in the solar wind send hydromagnetic disturbances. So on the solar corona send hydromagnetic disturbances out into the solar wind, which can interrupt radio communications on Earth. Where are we? There we go. Sorry, that's where I was. Yeah, can that interrupt radio communications on Earth? And in fact, even a gamma ray burst, I should say parenthetically, its effect on the atmosphere has been measured, and so it can rattle our magnetosphere. But we should be more worried about solar flares rather than gamma ray bursts in terms of having yet another thing to worry about. Anyway, to go back to the slide that got out of order, the challenge, if you like, for the fast radio burst business is to explain how one of these radio waves, which has wavelengths, say, of order kilometers or so, is going to make coherent radio emission with wavelengths of order centimeters to meters, say. And the idea is that basically these waves, which are probably linear in the sense that their amplitudes are less than the full field strength at the surface, they will become nonlinear at roughly 10 to 30 stellar radii, say 100 to 300 kilometers, and the strengths of the electric fields are about 10 teravolts per meter fields. And the strengths where this happens, the strengths of the magnetic fields are comparable with this 100 megateslas that you see in a regular neutron star. That'll be the strength of the field in the wave, where I assert that is all the action is going on. Now, when the radio astronomers measure the strength of these particles, of these bursts as in terms of brightness temperature, what they're really saying is the energy per mode in phase space is KT, where T is 10 to the 20 to 30 degrees for a pulsar and 10 to the 30 to 40, as I said, for an FRB. And this, of course, is much, and they're impressed that this is much more than the energy of the electrons and positrons that you have there. And so they say it's a coherent process, all true, all correct. But I would say probably a somewhat misleading way to think about it. If one thinks about an earthquake, you don't talk about the brightness temperature of the earthquake. You don't relate the energy in that disturbance to the energy, say, of a silicate molecule or something. If you talk about Albert Einstein playing his violin, you aren't worried about nitrogen and oxygen molecules. You're just seeing, if he's playing fortissimo, you're just seeing large amplitude linear wave modes with lots of energy in them. Same for the solar flare. Again, you wouldn't think about this in terms of the temperature of the radioactive electrons. And if you go, obviously I'm looking in an Aristotelian way at earth, air, fire, and water. You look at a tsunami, an oceanographer is not fussed about the fact that there are water molecules there. An oceanographer really doesn't know that and understand that, but it's kind of irrelevant to their describing and predicting tsunamis. And so, but nonetheless, this sort of outlook has in some sense colored the interpretation of pulsar radio emission, by extension the FRB radio emission. So one tends to think about either what's sometimes called curvature radiation, which is a bunch of electrons that are somehow or other bunched together and move along curved trajectories, rather like a giant electron might do in a synchrotron. And as it's being accelerated, it will emit radio waves as a result of moving with Lorentz factors of hundreds to thousands, say, along a field line moving along the field line because everything's in its ground state of gyrational motion under these circumstances. So it moves along the field line just like a giant charge moving in a synchrotron. But in this case, you're moving along the field, not perpendicular to the field, but it's still an accelerated motion, and you get, in that case, a wavelength that's gamma to the -3, where gamma is the Lorentz factor times the radius curvature of the orbit. So that's one class of models for pulsars and FRBs, and the other one, which is becoming more popular, masers. And here what you have is you acknowledge you've got a plasma here, you've not got a Maxwellian distribution, you've got a plasma through which there are streams of fast particles that make it a highly non-equilibrium distribution function. And that lack of equilibrium allows there to be essentially a population inversion, if you like, and that allows small amplitude electromagnetic waves, plasma waves, to grow at an exponential rate and act as essentially a continuous wave maser. And those are the two types of mechanisms that are being proposed. And you know, I've actually collaborated on papers on both of these, and I'd like to sort of propose that maybe this is a little bit misleading, and we should try and think about this the way that the Earth, Air, Fire, and Water Brigade think about their problems. So, that's the slide I just discussed. So let me talk a little bit more about how to do this. And so here I'm going to look at electrodynamics in the same way that a fluid mechanics physicist or engineer would look at their subject. And I'm going to go back to, well, both Faraday, but especially Clerk Maxwell. If you go to his, his treatise in electrodynamics and his papers and so on, he really thought about current as a continuous fluid. Electrical current is a continuous fluid. It's nothing to do with particles. That didn't happen. And well, Heaviside was probably the first person to sort of work this out in a sensible way in the 1880s, long after Maxwell had died. And it wasn't until 1895 that the Larmor force came along. And you have to believe that Maxwell, who contributed so much to the kinetic theory of gases, would have contemplated, and he knew about Faraday's discovery of electric charge and so on, of charge in chemistry, electrochemical experiments and so on. So he knew about that for sure. And you have to believe that he thought about the electricity being carried by individual atom-like particles. But his description really sees this current as a continuous fluid. And if you just take the equations you have seen on a T-shirt somewhere in one form or another, and then supplement them with the very simple rule that there is no inertia associated with the plasma. The plasma is essentially no inertia, it's just there to provide charges and currents. Then the force density rho E plus J cross B, or equivalent to the divergence of the stress energy tensor, are going to vanish, and that leads immediately to a constitutive relation like this. It relates the current closely to the nonlinearly to the magnetic field. If you think about this and just think about simple linear waves or characteristics in this evolutionary system, then there are two modes. One is, I'll call it here an F mode. It's one polarization. It behaves just like an electromagnetic wave. It will behave in a WKB sense as a polarization with the electric field and the magnetic field perpendicular to the wave vector traveling at the speed of light. And so he doesn't really notice the magnetic field. And then the other polarization I call an S, or a slow mode. And that's one where for a wave vector at an angle theta to the line of sight, the phase velocity is c cosine theta, but the group velocity is still c, but the energy travels along the background magnetic field, but the wave fronts move across the magnetic field lines. And so these are the two simplest modes that you get out of and they carry the information in characteristics if you think about this, the hyperbolic system. And this automatically implies that there's no electric field along the magnetic field, actually not along the current either. I used the GR version of this in the description of black holes in the first lecture. And if you want to say, well, in practice, there is going to be a little bit of QE going on. It's a bit like the viscosity of water. If you're an oceanographer, you know water's got a little bit of viscosity, and that's important. Then you can add a little bit of E dot B, and you can develop this whole theory with a little bit of perturbative viscosity there, which can, in much the same way as it does in hydrodynamics, can lead to very interesting consequences. Again, I'm not going to deal with this. The only thing is I'm going to say here, and this is where I really am departing from much of the work that's done in this business, I'm strongly de-emphasizing the QED details rather than taking a reductionist view that you build up the macro phenomena from the consideration of the smallest microscopic phenomena. I'm going to say that's all takes care of itself. Let's just look at the macro physics. So you can go from the sins of emission to sins of transmission. The F mode will essentially just be a wave that travels at the speed of light. This is just a cartoon here. Many more sort of movies and so on, which I haven't got time to show. And essentially, this will just travel like an a large electromagnetic wave. But the S modes will move along the magnetic field at the speed of light, the curving magnetic field line. And if we just imagine looking at the expanding S modes from a disturbance on the surface of the neutron star, say right down here, might be a disturbance down there, it'll travel outwards along these field lines like that. Then you have to look at them at a given observer time. So all of the superluminal effects that I talked about in the context of jets will be apparent here too. So what you actually see, including the duration of these pulses, depends on where you stand and which mode you're looking at and so on. One thing I will say is that these modes don't steepen, but another thing is that the waves, which one would envisage as having something like 10% relative amplitudes at the source, at the surface of the star, will become nonlinear at about, say, 100 kilometers or so, because the energy is, for the slow mode certainly, will become nonlinear to 100 kilometers because the energy is carried along the expanding magnetic field lines, and it's going to look like a dipole at large enough distance. And so that basically means that delta B over B is going to increase as R to the 3/2, and that basically means that around about 100 kilometers or so, you're looking at delta B of order B. So this is a nonlinear wave. This is the tsunami breaking. And at this point, as I said, delta B is about 100 megateslas, like on the surface of a regular neutron star. And there's probably, in terms of potential difference across this disturbance, there's nearly a zettavolt up there. And so the vacuum, in some sense, is the perfect conductor. Now, this is the basic idea then at this point. Let's suppose we have some disturbance that looks a little bit like a solar flare. And it's a sort of ongoing disturbance. It doesn't just happen in one flash. It goes on, we don't know how long it goes on for, but it might be 10 microseconds. It might be a millisecond or so. It's going to make waves with characteristic wavelengths of about 1 kilometer or so. That'll be the size of the scale of the structure, and everything's moving at the speed of light in this magnetosphere. And they're going to make, so we're going to have a lot of F modes and a lot of S modes, and they're going to be propagating through this medium, making all the charges that they need. That's no problem. We just describe them in this macroscopic fluid mechanical way, if you like. And you're going to get waves that, if you follow them locally as in a sort of WKB sense out at, say, at 100 kilometers or so, you can start thinking about them as sort of in a geometrical optic sense, and then they're going to intersect. And at that point, as I said, they become nonlinear, but they become nonlinear in an important way. And we're talking here about the intersection of fast modes with fast modes, fast modes with slow modes, slow modes with slow modes, and so on. And you can have waves, it turns out you can have waves that are chasing each other and waves that are head-on confrontations, and those are different cases, and but you know, they can all be handled very well. And one way to do this is to Lorentz transform to make this into essentially, in terms of an intersection, to understand what's going on. It's a sort of is to Lorentz transform into a frame in which this becomes essentially a one-dimensional problem, and you can generally do this. And when you do this out at this region where the waves have become nonlinear, and so it means you've got, say, two waves with comparable amplitudes that are comparable with the background field, it's pretty obvious that you're going to make space-time zones where not only is the first electromagnetic invariant E dot B, not only does that vanish, but the second electromagnetic invariant, E squared minus B squared, can change sign. And whereas at the point of origin, it was a magnetically dominated environment, the electric field can be larger than the magnetic field. And it's actually more complicated than this, but this is the simplest thing to understand, is that if you just consider short wavelength waves in this environment under the force-free rules and don't ask questions about the QED, just assumes it does its job, then the short wavelength S modes, they will grow exponentially in this regime. And so we might start off with say, kilometer wavelength waves, but we'll have centimeter waves and meter waves that will also grow basically as S waves. They're sort of basically like S waves. And they grow in this regime exponentially very, very fast. And so in this sort of collision zone, still quite close to the surface of the neutron star, certainly in comparison with other models that have been thought about, you get short wavelength S modes that are created, and they'll grow exponentially. And they'll make a sort of a broadband radio wavelength, very, very high brightness in the radio astronomer's sense, very high brightness temperature spectrum, turbulent spectrum. And these waves, because they're S waves, they'll propagate along the magnetic field line, go away from this interaction zone, which is, it's only transient, it's only a region in space-time. Eventually, they'll get out to a radius, probably 1,000, 10,000 kilometers or so, when it is no longer possible to make charges at the rate that you need to carry the currents that are needed to support these S waves. At that point, they mode convert to electromagnetic waves, and so they just become like regular radio waves in vacuo, and they then propagate out into the surrounding medium. And so that's the sort of general idea of what you might be looking at generically in the fast radio bursts. And if you try and think about, I haven't got time to go through this in any more detail, than a lot of things I for one don't understand at all about this. But if we go back to the original problem of what makes radio pulses, we know how they pulse, but we don't know how they shine. How do they shine? And that still really is, I think, probably a largely unsolved problem. We're talking about currents in the pulsar magnetosphere that are about 10 teraamps and potential differences of petavolts and so on. So again, you make, as has been known for a very long time, you make charges, since the 60s, you make charges very easily through QED processes. And these happen, it's thought, in spark gaps of one form or another. And here the metaphor is that we're looking at some sort of electromagnetic thunder that's going to make these probably kilometer wavelength waves. And again, in these circumstances, and this is a very different view from the models that are mostly out there, colliding S waves, for example, it's not the only possibility, but it's one of them. They can make centimeter to meter wavelengths, and these will then mode convert to electromagnetic radio waves as they propagate away from the neutron star. So this says that perhaps the radio pulsar emission is, if you take this maverick or revisionist view of what caused the radio emission, then perhaps the pulsar radio emission can be made in the same sort of way as the FRBs by this rather different mechanism from coherent curvature radiation and radio masers. So just let me summarize at this point. I just make a few points. We know that many neutron stars are formed as magnetars with up to about 30 or maybe even 30 times the Schwinger field or so. So that makes them genuinely of interest in their own right. And they are, I would say, a prime candidate, but not a proven one, for the fast radio bursts. Other explanations may still be right for essentially all of them or just some of them. And so it's wise to have a very Catholic view of what's going on here. The particular model that I described here, which has a lot of common features with many other models, is that there are magnetic flares or quakes that launch these long wavelength waves into the magnetosphere. And what I would say is that fairly close to the neutron star surface, these essentially fluid-like processes create radio waves, whereas most of the other investigations have looked at these waves happening out much farther away from the surface of the neutron star. In some cases, they're out at 10,000 times the radius of the neutron star. In other cases, they're right out in the wind, light months away from the neutron star. And so many of the papers say there's maser emission going on in essentially expanding shock fronts in very distant winds. And in the version that I had, this may convert to electromagnetic waves and may apply to, could also apply, these ideas could also be applicable to pulsars. So let me finish at that point. Thank you very much, and please keep well.
So thank you very much for this beautiful talk. We have time for questions. So please raise your hands if you, so someone raised this. So we have a question, So just ask your question, yes. Go ahead.
Yes, it's about the coherence of the emissions. So you mentioned at the beginning that the emission is coherent. So at the end, you spoke about turbulence spectrum, and I do not understand how a turbulence spectrum can be coherent.
Okay. I think we're talking probably about different uses of the word coherent in different subfields of science. And I'm keenly aware of it, and I think it's totally reprehensible. But in a business where we can't even use the same units, we have to get along with it. When a radio astronomer says that the pulsar emission is coherent, what they really mean is they're looking at broadband distribution of radio emission. And so, but it's very high brightness temperature. By coherent, what they mean is that their sources are lots of electrons in the standard view that are acting together. Mm-hmm. So it's coherent from the point of view of the electron distribution function. Now, if you're looking at, it's actually more complicated than this, because we do know a lot about the frequency structure of individual radio pulses, say from regular radio pulsars, and it does have frequency structure, and some of that is a propagation effect. Some of that is caused by refraction and scintillation in the interstellar and intergalactic media. But generally, if you have a lot, let's take the simplest case, which is the coherent curvature emission, and there, what's imagined in the most simple-minded way is a giant electron with, maybe 10 to the 20 electrons behaving like one large electron created by some sort of plasma instability. And we imagine that in some Jacksonian way propagating along a curved trajectory and creating a Liénard-Wiescher potential in the far field. Now, that's a very broad band electromagnetic wave that the observer sees, with the spectrum going as nu to the 1/3 and then exponential above the critical frequency. And so that's what the observer sees. So the coherence is really in the electron distribution rather than the electromagnetic wave. So that's what's going on here. And it's basically semantic. But thanks very much for the question, because that allowed me to make that point clear.
Okay, thank you very much. So it has nothing to do with coherent light.
Well, it's not. It's radio waves. It's not coherent. Yes. So we're very much longer wavelengths. Now, it could be there are coherent processes that are happening at optical wavelengths, but most of the ones that are known, first probably discovered in Jupiter, but also seen in the sun, you know, you've got coherent processes in the radio astronomer sense in Jupiter and the Sun. You don't have to go to pulsars for that.
Okay, thank you.
Other question? Well, maybe I have one, but that's more about my ignorance concerning force-free electrodynamics. So you showed an expression for the current in terms of the fields of E and B. Is there a similar looking expression for rho? For the
Yes. Oh, let me.
Is it obvious that the conservation equation is fulfilled? I mean, or
Okay,
maybe I didn't pay attention.
No, I'm just. This again. This is. Thank you so much, Mark. This is a important point. Let me go back to. Sorry. Go back to this these equations here. These are, as one commonly says, Maxwell's equations in units in which pi is set equal to a quarter. That's a joke. But they work here. They actually do have a name. These unit systems, and they work fine here. And so these are, you recognize these Maxwell's equations.
Yes. Uh-huh.
Now, and in fact, this development is to some extent it's in the treatise. You won't find any Lorentz force there, but you will find part of the way along this road, particularly Maxwell stress tensor, of course, and so on. So if you then say that the only dynamics going on is electromagnetic field pushing classical electromagnetic inertia around, there's no inertia there, there's no fluid to resist it, then rho E plus J cross B will vanish, the total force density, this is of course in the treatise, or equivalently the divergence of the stress energy tensor written here is a 3+1 form, but it's just the same for a 4-dimensional space-time.
Okay.
Then if you then say this implies two things, one is E dot J vanishes, which means there's nothing to do any work on. If you were writing out Poynting's theorem, actually Poynting's theorem is not in the treatise. It was Poynting was Maxwell's student, and he published this in, I think, in 1888 or something, or after Maxwell died. So maybe it was his thesis problem, and Maxwell. I'm sure Maxwell knew it, but energy was not so important in the 1860s as the pushing and pulling around of forces. If you then, sorry, the two things here, one is E dot J vanishes, which is, as there's nothing to give energy to, so it has to vanish. And then E dot B vanishes.
Mm-hmm.
So there's no electric field along the magnetic field in this strict formalism. And then if you then say, well, not only does E dot B vanish today, it'll vanish tomorrow too. That means d by dt of E dot B vanishes. So you just dot an E into that and a B into that, mm-hmm. and add them, and you then get this.
Okay.
Actually, I'll add one thought, and this is actually essential to dealing with the force-free electrodynamics, the interaction region. It isn't just a question of being the time derivative of V dot B vanishing. It's also the spatial derivative vanishing is important. And so we take the gradient of E dot B equals 0, you get other equations which are necessary to solve 1D evolutionary equations.
Okay.
So that's how that works. And you said something about conservation.
Mm-hmm.
Was that okay with the talking about the stress energy tensor?
At least I understand the derivation. Yes, thank you. Mm-hmm. Yes.
And sorry, you said about charge density. So yes, that's here. Div E rho.
There, yes. Mm-hmm.
And there's two components to the current density. One is an E cross B drift of the charge density, and the other is a part along, which is perpendicular to the magnetic field, and the other is a part along the magnetic field that has to be there to keep E dot B 0.
Okay. Thank you. Any other question? Well, if not, let's thank Roger again for this talk, and then we will reconvene virtually next week on Tuesday, 23rd of March, for ultra-high cosmic rays. So